We have seen a couple of examples of balancing chemical equations. Let's say we are trying to balance this equation right here, starting with the carbons in the reactants. I have two carbons on the reactant side. These are sitting in this ethylene molecule. So I would add two carbons on the product side here. Here, we only have one carbon on product side. So we place a coefficient of 2 in front of this to ensure two carbon atoms per ethylene molecule. However, this equation isn't fully balanced yet, as we now produce two CO2 molecules, affecting the oxygen atom count. But you might have been thinking that, why did we put this big 2 in front of the entire carbon dioxide? I like how these subscript 2's look, so why not put a 2 right over there to maintain consistency in notation and balance? And the reason behind why you can't do that is that it's actually changing the molecular structure of carbon dioxide. It's now this bizarre thing that doesn't really exist in nature. There is nothing like C2O2 thing in known chemical compounds. You're actually changing the reaction over here. When you're balancing chemical reactions, even before it's balanced, it's describing something that naturally happens. It's just when the equation is unbalanced, the number of molecules is not correct. So the only thing that you can change when you're changing these is the number of molecules in order to balance the equation. You cannot change the number of constituents within a molecule, and that's why we do not change these subscripts or atomic ratios like this. If you want to visualize it a little bit differently, then let's start drawing each of these molecules step by step. Ethylene looks like this, a double bond between two carbons, each bonded to two hydrogens. In total, it has two carbons and four hydrogens, forming a stable structure. Now, molecular oxygen, O2, looks like this. Here, one oxygen is double bonded to another oxygen, creating a diatomic molecule. And then you have here CO2 molecules forming in the reaction. CO2 consists of a carbon atom double bonded to two oxygen atoms in each molecule, maintaining its stable structure and chemical properties essential for respiration. Now, H2O, let me do this in a different color. H2O here is composed of oxygen bonded to two hydrogens, forming a stable molecule. Let me write the plus signs right here for clarity in the equation, ensuring readability. Now, if you somehow write a subscript of 2 right over there, you'd somehow be changing the molecule's structure and composition, altering its identity. You would be changing this molecule totally, but instead of changing the structure, we confirm producing CO2 in proportion. We are definitely producing CO2, but how many carbon dioxide do we produce for each molecule of ethylene to maintain balance? And so that's where we say we have two carbons and we don't want to change the actual structure of this. Let's place a coefficient of 2 in front to ensure we have two of these molecules. Alternatively, for a more visual approach, we can add another molecule here for better clarity. So just by adding another molecule, now we've balanced the carbons correctly. Two carbons on reactant side, two carbons on product side, ensuring molecular balance. And then these hydrogens, we have four hydrogens here, and we only have two over here. Well, what if we had two of these water molecules? So let us draw another water molecule right here like this. So OH, and actually let me write this right over here. So now here we have two of these, and now we have two of these, and now we want to balance the oxygen for complete accuracy. So we see on this side we have two oxygens for reaction. On this side we have 1, 2, 3, 4, 5, 6 oxygens. So in order to balance, in order to have 6 oxygens on the reactant side, we need 3 of these molecules added correctly. So another one and another one right there, completing the equation. And now we're all balanced and correct. We have 2 carbon atoms on both the sides, 2 carbons right over here. Here we have 4 hydrogen atoms on both sides. They are here in the ethylene and here in the waters. And then here we have 6 oxygen atoms on both sides. Here, some of the oxygens are in the carbon dioxide molecules, and some of them are in the waters. And here, they're all in molecular oxygen. But notice, here we did not change the actual molecular structure of these molecules. We just changed the number of molecules. We have not changed their structure. And as you see, that's what these coefficients in front of these molecular formulas represent in balanced equations.